In this video we will talk about tension and the law of conservation of momentum. Before starting, please subscribe to my channel for more informative videos. Firstly, you should understand the easy concept of tension. Every physical object which is in contact exerts some force on one another. These contact forces are assigned names based on the kind of objects. Let's consider a person standing at some distance trying to pull a box. Well, here question arises that how the person will pull this box. The person will pull this object with the help of a rope. Thus we learn that any object can be pulled through some distance by a string, a rope, or a cable. When you pull the rope, you exert a force on it in your direction. This transmits a force to this box, which results the box to move in your direction. To simplify further here, we will assume that the spring is massless, meaning the mass of this rope is zero, which isn't true in real, but in front of the mass of the box, the mass of the rope is neglected. Now this force acting on the rope is given a special term in physics known as tension. So tension can also be referred as the pulling force. Tension is the force transmitted through a rope, string, or wire when pulled by forces acting from opposite sides. Tension can be defined as an action-reaction pair of forces acting at each end of the said elements. For example, ropes when pulled from two ends generates a tension force. This tension is a result of the forces applied by each hand trying to stretch the rope. The greater the force applied by each hand, the higher the tension in the rope. Similarly, when a block is hung from a string, the string experiences tension. This example of tension in a string is common in various scenarios, such as when objects are suspended or when weights are lifted using pulleys or other mechanical systems. Let's consider a box of mass m. When you pull this box in your direction, acceleration A will be produced in the same direction as force. The net force on this box will no longer be zero. This acceleration is produced due to the tension T1 in the string caused by pulling the box. According to Newton's second law of motion, F equals ma. Here tension T1 is a pulling force which produces acceleration A in the box of mass m. Thus we can write Newton's second law of motion in terms of tension as T1 equals ma. This means that if the net tension is not zero, acceleration will be produced in mass m, where T stands for tension force and m denotes mass, kilogram. This formula is utilized if the mass being dragged by the rope also has acceleration. If there is no acceleration, then the weight of the body equals the tension in the rope. If we talk about the vertical motion of two bodies attached to the ends of a string that passes over a frictionless pulley, we see two bodies A and B of masses m1 and m2 respectively. Let m1 be greater than m2. The bodies are attached to the opposite ends of an inextensible string. The string passes over a frictionless pulley as shown. The body A being heavier must be moving downwards with some acceleration. Let this acceleration be A. At the same time, the body B attached to the other end of the string moves up with the same acceleration A. As the pulley is frictionless, hence tension will be the same throughout the string. Let the tension in the string be T. Since the body A moves downwards, hence its weight m1g is greater than the tension T in the string. T net force acting on the body will be A equals m1g minus T. According to Newton's second law of motion, m1g minus T equals m1a. As body B moves upwards, hence its weight m2g is less than the tension T in the string. Net force acting on body B equals T minus m2g. According to Newton's second law of motion, T minus m2g equals m2a. Adding equation 1 and 2, we get acceleration A. A equals m1 minus m2 divided by m1 plus m2 into g. Similarly, if we divide equation 2 by 1, we get tension T in the string as T equals 2m1 m2 divided by m1 plus m2 into g. This arrangement is known as Atwood machine. It can be used to find the acceleration g due to gravity given as g equals 2m1 plus m2 divided by m1 minus m2 into a. Now if we talk about the motion of masses attached to a string that passes over a frictionless pulley, we take two bodies A and B of masses m1 and m2 respectively. Let the body A moves downwards with an acceleration A. Since the string is inextensible, therefore, body B also moves over the horizontal surface with the same acceleration A. as the pulley is frictionless, hence tension T will be the same throughout the string. Since body A moves downwards, therefore, its weight m1g is greater than the tension T in the string. Net force acting on body A equals m1g minus T. According to Newton's second law of motion, m1g minus T equals m1a. The forces acting on body B are weight m2g of the body B acting downward, reaction R of the horizontal surface acting on body B in the upwards direction, tension T in the string pulling the body B horizontally over the smooth surface. As body B has no vertical motion, hence resultant of vertical forces, m2g and R, must be zero. Thus, the net force acting on body B is T. According to Newton's second law of motion, T equals m2a. Adding equation 3 and 4, we get acceleration as a equals m1 divided by m1 plus m2 into g. Putting the value of a in equation 4, we get tension T. T equals m1 into m2 divided by m1 plus m2 into g. Force and momentum are related by the fact that force is the rate at which momentum changes with respect to time. Momentum measures the motion content of an object. Force, on the other hand, is the push or pull that is applied to an object to change its momentum. Let us consider a body of mass m moving with initial velocity vi. Let a force F acts on the body which produces an acceleration a in it. This changes the velocity of the body. Let its final velocity after time becomes vf. If pi and pf be the initial momentum and final momentum of the body respectively, then pi equals mvf and pf equals mvf. Change in momentum equals initial momentum minus final momentum. Or we can write it as pf minus pi equals mvf minus mvi. Thus rate of change in momentum is given by pf minus pi divided by t equals mvf minus mvi divided by t. After simplifying results in m into vf minus vi divided by t. Since vf minus vi divided by t is the rate of change of velocity equal to the acceleration produced by the force F. Let's suppose pf minus pi divided by t equals ma. So according to Newton's second law of motion, we know that F equals ma. Or we can write it as pf minus pi divided by t equals F. This equation defines force and states Newton's second law of motion as when a force acts on a body, it produces an acceleration in the body and will be equal to the rate of change of momentum of the body. The law of conservation of momentum is one of the most prominent laws in physics, as we know that the momentum of a system depends on its mass and velocity. The conservation of momentum law principle tells us that the total momentum of a system is always conserved for an isolated system, where isolated system is defined as a group of interacting bodies on which no external force is acting. Therefore, momentum can neither be created nor destroyed. Law of conservation of momentum is given by the following equation. This equation shows that the momentum of an isolated system before and after collisions remains the same, which is the law of conservation of momentum. Law of conservation of momentum is an important law and has vast applications. We have noticed that whenever we fire a gun we observe a recoil, which is because of the law of conservation of momentum. As the bullet gains forward momentum we observed a backward momentum, motion, which is called the recoil. Similarly, the motion of the boat is based on the concept of the law of conservation of momentum, as when we push the water backward with the help of oars the boat is pushed forward because of the momentum. Having said so, the energy of a system is always conserved. One of the best applications of the law of conservation of momentum would be in space travel. There is no medium in space to exert a force on, then how do rockets travel? Well, they eject matter at a very high speed, so in an isolated system, the momentum should remain constant. Therefore, the rocket will move in the opposite direction with the same momentum as that of the exhaust. Thank you for watching. In next video we will talk about the force of friction and centripetal force. Please like, share and subscribe to my channel and press the bell icon to get new video updates.